what is involved in solving Einstein's equations of general relativity on the computer, and what we are currently capable of doing with these simulations in order to model, for example, gravitational waves for detectors such as LIGO and Virgo. And then we will switch probably towards the end of this lecture and also on Monday to studying neutron star, and black hole neutron star mergers, and all of the extra additional exciting physics that comes with the presence of a neutron star in these mergers. So as a quick reminder, numerical relativity, we are trying to evolve Einstein's equations of general relativity. So we take those complicated four-dimensional equations and we separated them into a spatial part and some coordinate choice for how time evolves and how the coordinate evolves. And with that separation of the metric in spatial and time parts in 3+1 formalism, we can actually write evolution equations for the metric and for its first time derivative or something very close to it. And the issues that I mentioned this morning, there is a big problem, which is how do we find that those coordinate choices, the choice for the lapse alpha and shift beta, if we don't know how space-time is going to evolve? How do we avoid running into singularities in our evolutions? And how do we stop the growth of the constraints that exist in Einstein's equation from small numerical errors? And then part that I won't discuss here is how to choose appropriate initial data. And let's say a little bit about how to get a well-posed problem. So there's a lot of things that come into finding solutions to these problems, and it took decades for the numerical relativity community to actually figure that out. From basically as soon as Einstein's equation started to be attempted to be put on a computer to about 2005, when black hole mergers were for the first time performed on the computer. And there is far too much going on there for me to be able to give you every single point of detail of how Einstein's equation can be put on the computer. But I want to choose a few select topics that are also useful in other fields of astronomy and physics occasionally, and that can be of particular interest. I'll talk a little bit about what constraint damping is and how it's used. It's used both in general relativity and actually in some cases in magnetohydrodynamics simulations. I'll talk a little bit about how codes avoid dealing with singularities, and I'll also show you how equations can be rewritten in a form that is particularly convenient for evolution equations. And in the case of Einstein's equations, we wanted them to be put in what is called symmetric hyperbolic form. So I'm going to start with that. If you have a set of equations, let's say that you have a vector u here, and you can write it in first order form, in the form in which the time derivative of u is some linear combination of the spatial derivatives of u plus some source terms. Right? Well, we say that that equation is strongly hyperbolic if for any direction, which I write w here, the matrix A here for derivatives in that direction is diagonalizable, which means that it has also real eigenvalues. And I'm going to show an example of how that works for an equation for which we already know what the answer is, but that can serve in illustrating our purpose here. I'm going to look at the wave equation, which, like Einstein's equation of general relativity, is a second order equation in both time and space. Now, if I wanted to change that into a first order equation, the first thing that I would need to do is define new variables that are the derivatives of u. And I can define, let me make sure that you define them the same way, v as the partial derivative of u with respect to time, and w as the partial derivative of u with respect to space. And then I can write these equations as first order equations for now a vector of variable instead of a single variable. So I have more variables, but I'm down to a first order equation, which is easier to do on a computer. Right? So my equations now are w dot, or let's see, delta tw, well, delta x v, right? This is saying that the time derivative of w is the time derivative of the spatial derivative of u, which is also the spatial derivative of time derivative of u, which is the spatial derivative of v. It's just changing the ordering of partial derivatives. And delta t of v, similarly, is delta x of w. Right? Of course, if I do that for Einstein's equations of general relativity, it's going to be a lot more complicated because there are a lot more variables. But I can also reduce them to a first law form in time at least. And now, if I look at what that matrix would be here, right? Well, it would be the derivative, the time derivative of w does not depend on the spatial derivative of w, but only on the spatial derivative of v, whereas if I put it on the left-hand side, a -1 sign. And similarly, the time derivative of v does not depend on the spatial derivative of v, so the diagonal term is 0, but it depends on the spatial derivative of w with the -1 sign. This is saying that this is the same thing as saying that tw delta t v equal a matrix A acting on this minus A in this case. If I put it on the right hand side. Now this matrix is actually diagonalizable and has real eigenvalues. I can solve the eigenvalue problem. What I'm going to find is that minus v lambda w equal lambda v. So the solution to the eigenvalue problem, there are two of them. It's either lambda equal +1, v equal minus w, or lambda equal -1 and v equal plus w. And what is going to happen for these hyperbolic problems is that the eigenvalues actually give me the speed at which information propagates through space-time. In this case, both modes of my equations are going to propagate at the speed of 1. In general relativity, generally we take the speed of 1 to be the speed of light, but this could be anything. If it was a sound speed, maybe it's the speed of sound. And the mode that is actually propagating at the speed lambda is the eigenmode of the matrix A, which has that eigenvalue. So I have a mode, say, x plus, which is in these coordinates, let's say, if I normalize it, 1 over square root of 2 and minus 1 over square root of 2, and a mode x minus, right? In this one, v is minus w, and in this one, v is plus w. And this is roughly what you would expect for the wave equation. You have two possible waves, one moving at the speed of 1 to the right, one moving at the speed of 1 to the left. We already knew that for this system because it's a system that is extensively studied in physics. But if I had a more complex system, I could similarly find the eigenvalues of that matrix A and figure out what the eigenvectors are. And I would know that I have a mode that goes at a certain speed in a certain direction for each of those eigenvalues. There's an advantage too if I try to impose a boundary condition on the problem. Let's say that I have a problem where I try to solve something here, and then I have a boundary here, right? And I want to impose a boundary condition here such that there is no information coming into the domain. And I know that I have two modes. I know that there is a mode x plus, which is moving at a speed of 1 to the right, and the mode x minus, which is moving at a speed of 1 to the left. And so, and my solution, my general solution, u, has to be some combination of these two at any point. Just by superposition of the solutions. Well, what I know, if I want to avoid sending waves into my system, all I need to do at this boundary is to set x minus to 0. And that means that only x plus is non-zero. That means that I want at boundary I want so x plus is non-zero, so I want v equal minus w. I cannot have a mode. I cannot have a mode which contributes to this left-going mode here, which is actually the condition that you would expect for no incoming wave at this boundary, because it's also given the definition of v and w. Let's see, delta t u equal minus delta x u. Or u is some function of x minus t, which is exactly what a right-going wave is as a solution to this problem. There cannot be a left-going wave which will be a function of x plus t, which would be the other mode. So this is it's a convenient way to know how information propagates through your system, but it has also other advantages. We know that so the eigenvectors of that matrix, which we call the characteristic modes, are going to travel as a wave at a known speed, and that speed is real. Now, it's a real number. It means that locally, at least, there is no growth or damping of those modes. So it also evolves in a stable manner through your simulation. If there was an imaginary component that would lead to growth or damping of the mode. You can apply boundary conditions using the eigenvalue decomposition. You can communicate between different regions of a computational domain. If you have an interface and you want to place one part of the interface on one computer, the other part on the other, these eigenmodes tells you which information has to come from the left side and which information has to come from the right side. And importantly as well, there is a lot of analytical work that has been done on that kind of equations. And among other things, there are known conditions that tell you what is required for equations like that to avoid forming shocks, which is nice. So, and in the case of Einstein's equations of general relativity, particularly, it's possible to construct the equations in such a way that you are not going to form shocks in your evolution. So everything is going to remain smooth as long as you start from smooth initial conditions. That allows you to get more accurate solutions to the problem. So that's a common thing that is useful to do if you are evolving, trying to evolve higher order equations. You go to a lower order formulation, and then you try to put it in a mathematical form that is practically stable and easy to handle using computational methods. Another thing that was necessary for general relativity, but that is also useful in other contexts, is constraint damping. Constraint damping means that it's something that you want to do when you have those evolution equations, and then some constraint that has to be satisfied at every time in your evolution. In the case of magnetic fields, for example, that would be the constraint that the divergence of the magnetic field is 0 everywhere. And as we've already discussed, if you start with a very small divergence of B, but non-zero, it can grow very rapidly in your simulations. In general relativity, the constraints that you have, which are much more complicated, can also grow. But there is a way to avoid this issue by introducing a new variable which grows if the constraint is not satisfied, and to write evolution equations of that variable so that now both the constrained varying mode and the new variable evolve as wave in your system. So both of those, here the longitudinal component of B, the one that violates the divergence B equals 0 constraint, and that new variable phi are now moving as waves in your computational domain. And if I add that gamma phi term there, I also can make them damped wave, which is even better, because then my constraint varying mode, not only do they propagate away, but they are also killed as time evolves. And at the same time, when divergence b is 0, this is exactly the original Maxwell's equations. So as long as the constraints are initially satisfied, if the constraints were exactly satisfied, these equations will be the same as Maxwell's equations. And when they are not, they are damped back towards a physically acceptable solution. For Maxwell's equations, with just the magnetic field divergence being the constraint here, it's only one extra variable. For Einstein's equation, it's a much more complicated problem because there are a lot of constraints and they take a form which is a lot more complicated than that. But the general idea is the same, is that you add new variables and you use them to damp the unphysical modes and let them propagate away from the interesting part of your system. Okay. So that's the mathematical aspect of the problem. For solving the singularity issue, there are basically two methods that have been used by numerical relativists. One is to remove the black hole from your simulation and count on the fact that there should be around the black hole a region surrounded by, limited by the event horizon of the black hole from which no information escape. So presumably, whatever I do inside of that region has no effect on the outside. That's the general idea. And so if I remove a region which is inside of the event horizon from my simulations, including the place where the singularity would be, it shouldn't matter to whatever happens outside. And we only really care about what happens outside of the black hole because that's what we are observing. In practice, it's a little bit more complicated because the evolution equations actually can become unstable if you choose a surface inside from which information is flowing out and then possibly flowing back in without getting out of the horizon. So you actually have to choose that excision surface very carefully, and there's a lot of work that went into that, so that it is as close to possible as as close to the horizon as is possible, so that all information, all of the characteristic modes of those equations fall into the excised region. But that's the general idea, is you remove the black hole from your simulation, and you count on the fact that you don't need to know what's happening inside because all of the information is falling in. I'm also going to note on this plot, you can see that another important aspect in numerical simulations is to choose grids that match fairly well the geometry of the system that you are considering. And they can get pretty messy sometimes. You can see here, this is one of the grids that we use in our simulations of binary black holes. And you sort of make use of the spherical symmetry around the black hole to reduce the computational cost, because you know that the solution near the black holes and far away also from the black holes is nearly spherically symmetric. And then in between the black holes, well, there everything is unknown, and you cannot make use of approximate symmetries at all. And when the black holes get close to merger, on the other hand, those grids can get pretty messy. That's the bottom part of the plot. The other way to deal with the black hole singularity is to not deal with the black hole singularity and hope that it works. And surprisingly, occasionally it does. So I'm going to give you what the solution is and why it works. But one thing to keep in mind is that at the time it was done in the simulation, it was done by accident, and people did not know that it was going to work. They were very surprised when it did. It was not really meant to be used in this way. But as it happens, you can evolve a singularity on the computational grid without problem if you make smart choices, even by accident. The general idea is that you take your metric, which would at the center of a black hole be infinite, and you write it as the ratio of two finite numbers, with chi, the denominator here, going to 0 at the center of the black hole. Okay, that's not an accident. That was told true, and that makes a lot of sense. Is that you are trying to actually evolve finite quantities. And we know that that function chi actually at the center of a black hole can be made continuous, which is convenient. Now, what people were originally aiming to do with this was to keep the black hole fixed on your grid, and because you knew what the form of the singularity was at the center of the black hole, you would just remove that analytically from your solutions and evolve with the black hole fixed on your grid with some smart choice of coordinate evolution that kept the black hole in place. That didn't work because the coordinates were becoming very distorted as the black hole were moving and coming together, and you were trying to keep them fixed on your grid, so your coordinates were getting really messed up. The equations that they actually used for evolving the black hole don't matter much, but the general idea that to make this work, actually, you have to let the black hole fly. You have to let it move on your grid. And so I thought that this would not work because then we would have a moving singularity through the grid. But it happens that there is a choice of evolution of the coordinates, so those lapse and shift, which actually does keep the puncture, the singularity, well behaved. And those are the ones shown here. The actual form doesn't matter much, but the lapse condition, the one on alpha, is something that makes sure that as you get close to a singularity, your evolution slows down. And you stop taking big time steps. You take smaller and smaller time steps, effectively. And so you avoid getting to the singularity by just stopping to evolve. That, in theory, would not be a very great way of doing things because other parts of the grid will keep evolving, and your coordinates will become very, very stretched. But there is an alternative coordinate on the shift, which is the one that moves your coordinates around. And there is actually a very smart idea there, is that you can define an action which is the amount of distortion of your grid, which is a function of the time derivative of the metric. So it's something that measures how much your coordinate points are moving away from each other, not in the coordinate of your simulation, but actually by measuring the distances between those points as an observer there would measure them. And you can write an action which is the total amount of distortion of your grid, of changes in those coordinate distances over your entire computational domain. And you can minimize that quantity. And if you minimize that quantity, you're making a choice which effectively minimizes how much your grid is being distorted. That's a very complicated equations which we don't want to solve during evolution at each time step. But actually, you can write an evolution equation for the shift which approximates pretty well that optimal solution. And that's what was done here. And those two things in combination with the accident of letting your black hole run on your grid actually happen to work. Now, a few years after this was done, people started to understand why it works. And this is not showing very well at all. So I'm going to draw it. The initial conditions that you start from in the puncture data is effectively a wormhole. You don't start with a slice that goes all the way to the singularity of the black hole, but you start with what is known as an extended version of Schwarzschild or Kerr's metric, which you go through a throat here, and then the other side here is another whole asymptotically flat universe on the other side of the black hole. Okay? So this part here at the top is our universe, and this part here is someone else's universe, maybe, who knows. We can't go through it anyway because we would have to go through the black hole. And on your numerical grid, this is infinity. This is the location of the horizon, roughly. Actually, the horizon is somewhere here. There's another horizon here, but actually all of this is within, on your grid. You have the horizon here, and all of the other universe is within that small region. It has been contracted to nearly nothing on your grid. Right. And that's what you start from, and it actually evolves under those gauge conditions to a stable configuration in which that entire universe contracts to something that gets elongated here, but doesn't actually get out of the black hole. And your coordinates just evolve that small part of the asymptotic universe there and remain there. And you still have all of the outer part of our universe, and then inside, whatever is inside, is that small part of the wormhole that remains on your grid. And it has been now demonstrated that with the with the evolution of the lapse and shift that were shown on the last plot, this solution is actually asymptotically stationary. Now, actually, that has been used now to, instead of starting from the left and then going to the right, just starting from the right configuration and avoiding some annoying transients in your simulation. But that turns out to be a lot harder to do. But that's the general idea, is that you can actually evolve something not by excising the black hole from your region, by choosing a slicing of space-time, which never actually gets to the singularity, but actually remains more or less within that wormhole. Okay, so those are the main ingredients that were necessary to get to evolving Einstein's equations on a computer, was finding a proper evolution of the lapse and shift, finding a way to avoid a singularity, doing constraint damping, and putting the equations in first order symmetric hyperbolic form, or at least something that is equivalent to that. There are basically two ways in which it was done, and I'm not going to go into details describing them, but they end up being a pretty complicated set of equations, which this one was the first one derived. It's a generalization of the 3+1 formalisms that we have seen before, with a few extra variables to get to first order. And it was not derived with the idea of being symmetric hyperbolic, of having the right mathematical properties, but since then it has been demonstrated that it actually does have the right mathematical properties. The actual form doesn't matter. And there's another one which is even more complicated, which was explicitly derived starting from the idea that it should be symmetric hyperbolic, starting from the idea that it should have the right mathematical properties, and is used by another part of the numerical relativity community. Okay, I don't want to actually discuss what the equations look like more than that, because there isn't much information there for you. Any question on the numerical aspects of this? Otherwise, I actually move to what actually the simulations look like, and then neutron stars. Okay. So with those changes, numerical simulations actually became possible. Numerical simulations of merging black holes became possible. The first one was done in 2005 by Francois. It's shown here. And at the time, you know, it was a huge breakthrough. It's the first time that black holes were merged on a computer. Also, the waveform only covers, you know, about one orbit. And if you see the difference between the evolution of the three resolution here, the green, blue, and black curve, see that there is a very significant numerical uncertainty in the outcome of the simulation. But you know, that was the first time it was done. So just actually merging the black holes was a big result in itself. And you could already get predictions for the gravitational waves, also only really just for the merger part, of course, because that's the only part that was evolved. Interestingly, so this used the second formulation that I showed, and excision of the black hole. Within a few months of that, there were two other simulations using completely different methods that also solved the same problem. It's a bit surprising that they all came at the same time, but by the Brownsville Rochester group and by the NASA group. And you can see that all of those are fairly similar in that they evolve about one orbit of the black hole up to merger, leading to very similar gravitational wave signal. And the gravitational wave signal, I mean, still looks very much like this if you do a merger today with more advanced numerical methods. So from not being able to do mergers at all, within a few months, there were actually 3 numerical codes that were capable of doing these mergers. And this is mostly due to actually understanding all of these extra pieces that had to come to actually do merger simulations. Say that most often that 2005 set of simulations is mentioned as the big breakthrough in numerical relativity. But it was actually possible to do mergers multiple years before that. In 2000, Shibata and Oryu had already done neutron star merger simulations with multiple equations of states that still look a lot like what we obtain today in neutron star merger simulations. And so saying that numerical relativity started in 2005 is a little bit misleading, because it was also already possible to do neutron star mergers fairly well, if with much less accuracy than we can now, 5 years before that was possible. Because neutron stars are just easier. You don't have to deal with the singularity. They are harder because of all the physics that you want to put in there, but they didn't worry about that at the time. They used very simple physics. And so if you don't worry about all the extra physics, magnetic fields, neutrinos, and so on that goes into neutron star, they're actually a little bit easier to do. Those simulations all stopped as soon as the black hole formed, because no one knew how to evolve a black hole at the time. All right. So today there has been a lot of progress in the ability of numerical codes to actually do these simulations. And there are basically, I would say, two main groups of codes using very different methods. There's a set of codes that use finite difference method, so Cartesian grids with refinements generally. And that include probably the easiest one to get into, which is the Einstein toolkit, which is not what I'm using, but is, I have to say, the one that is the easiest to actually start working with, because it's publicly available, and it has fairly good tutorials and good support from the organizers of the Einstein toolkit. So it's certainly the most approachable tool in numerical relativity today. They all use the first form of the equation, the BSSN form of the equation, and fairly high order numerical methods, but finite volume. So they can get to pretty high accuracy with that now. The spectral methods, on the other hand, work completely differently. That works by expanding your solution on a set of basis functions, if you're not familiar with spectral methods. The advantage of spectral methods is that if the solution is smooth, and general relativity without matter is smooth, except at the black hole, of course, you get exponential convergence of the solution with the number of grid points as opposed to polynomial. So the accuracy of your code becomes a lot better with less resources if you are using spectral methods. The price to pay is that it might be high accuracy, but it has very low robustness. You make a small mistake in the formulation of your equations, you introduce a small error in your system, and everything blows up. So typically, every result in numerical relativity has been first obtained with finite difference code, and then got with more accuracy with spectral methods later. Because spectral methods, it just takes a while to get to the point where you can robustly do any system at all. A million flies here. Okay, so what can numerical simulations do? Well, for black hole, it's fairly straightforward to do a fairly wide range of systems that covers the interesting space for LIGO of black hole binaries. You can very easily do mass ratio 1 to 5, maybe 10 without too much problem. And a black hole with moderate spin, so maybe 70% or 60% of the maximum spin. Those numbers that I put there are semi-arbitrary, but it's the order of magnitude. And of the order of 15 orbits before merger, so the last few part of the system. That's what pretty much any existing code right now can do if you just ask someone, can you give me that waveform? And they will tell you, can you wait 6 months for me to do the simulations? And then you will get the waveform. But it's not very complicated, it just takes time. And there are also codes that have generated hundreds of waveforms that cover as much of that parameter space as possible, which are available in template banks. And so if you have a project and you wonder, well, can I see what a waveform for this type of binary looks like? Most likely there is something in that database that is actually at least close to what you are trying to do if you are within that range of parameters. Right? Where really the work of numerical relativists nowadays is in pushing the boundaries of that parameter space. And in particular, you can think of going to higher mass ratio People have done up to mass ratio of 100 in that simulation on the left, but they only done like a few orbits because it takes a very, very long time. The time step of your evolution in numerical simulation is set by the size of the smallest object. And so the smaller the smallest object is compared to the big object, the longer it takes to do your simulation. And the more error you accumulate also as you evolve.
What about simulations of animals?
Sorry?
Of extreme mass ratio.
That's the most extreme. With full numerical relativity. So there's a different type of simulations which is used for really extreme mass ratio, coming from the infinite mass limit and try to come back towards lower mass ratio, lower Q, I guess, in that case. And those are simulations that start some perturbation of the metric, assuming the small object is a perturbation on the big object, and then try to get to higher and higher accuracy by increasing the perturbation level that you are considering. And those come from the other side. But it's extremely difficult to do at higher than first order. I think self-consistently it has only been done fully self-consistently to first order. And then there are some higher order terms that have been introduced in simulations, but they are not, and it's not the entire picture. So it's a very hard thing to do, actually. Mostly because in numerical relativity, once you have a formulation of Einstein's equations that work, you put it for any system and you just run it. Here, when you want to go to higher order, you have to actually do the analytical work of computing what your equations should be like. And that's a complicated thing to do. You can go to very, very high spin, but it's not very common. And generally, it's a big price to pay in terms of accuracy. You can only do that, actually, if you excise your black hole. The puncture doesn't work at that kind of high spin. It's not that the puncture itself. You can create a puncture with a very high spin, but it decays as it settles to a standard black hole. It decays to a spin that is of order of 0.92, I think. So if you want very, very high spin close to maximum, it doesn't work. Also, your black hole becomes very small, so your resolution requirement across the black hole becomes complicated. And there is actually one simulation that has done 175 orbits, which is basically the entire duration of a black hole signal of standard mass in LIGO. That was also an accident. Someone chose the wrong initial parameters, forgot about the simulation for a year, came back and said, oh, it just finished. And that's what it was. It's actually a very useful simulation because it's the only one that can compare to post-Newtonian theory through the entire LIGO band. But no one was expecting to spend that much computational resources on it, I think. It serves a purpose, no, even if it is not done on purpose. So this is actually the simulation that was used when I say that current simulations are good enough to handle LIGO events up to signal to noise of order 30 to 50. You can compare this simulation to the waveforms that LIGO is actually using in the same parameter range and see, well, when would we start seeing a difference? That's roughly where. And then, as I said, there is a large template bank. There's large template banks of black holes that have been generated. So, without getting into too much details, you can easily find binaries at any mass ratio, any spin. But because those simulations are created by humans, they tend to like round numbers. So, for example, you have a lot of different mass ratio but zero spin. A lot of simulations with the exact same spin on both black holes, a lot of simulations which have a spin of 0.5 or 0.7 or 0.9, and not random directions and random numbers, because humans tend to just generate whatever they think about first, which is round numbers. So now there is an effort to actually do simulations with randomly choosing the initial parameters, or not entirely randomly, but choosing them to occupy the parameter space more efficiently than this, so that we have a better coverage of the actual parameter space of binary black holes, and not the one we hold naturally in our head. This is the same by another collaborations, but again, there is like a few hundred binary black holes which cover a lot of parameter space, but again, you can see with some holes in where the parameter space is where the simulations are placed. All right. So we can now generate a fairly wide range of simulations for at least the 15 to 25 orbits range with accuracy that is sufficient for current LIGO and probably for most observations that LIGO is going to do in the next few years. This is not the only thing that numerical simulations have been used for. Even before LIGO was starting to take data, or was starting to observe binary black holes at least, numerical relativity had already made some very interesting predictions from an astrophysical point of view. The one that probably got the most publicity is the discovery of black hole kicks. The idea of a black hole kick is that if you have a binary black hole, as it emits gravitational waves, those waves contain energy and angular momentum, and they also remove linear momentum from the black hole. But if you're on a circular orbit, or even, and you average the loss of momentum over the entire orbit of the binary, that comes to linear momentum loss comes to zero. It lost a little bit on the right, a little bit on the left, and it averages to nothing. But during the last plunge of the black hole, of the small black hole into the big black hole, for example, there is no cancellation of the linear momentum loss, and that means that you lose momentum to gravitational waves in one direction, and by conservation of momentum, your black hole is kicked in the opposite direction. And that kick can be pretty significant. If you choose your spins right, you can get to kicks of order of 5,000 kilometers per second for your black holes, which is enough to kick you off of many galaxies. And it's certainly enough, in most cases, to kick you out of small clusters within galaxies. So that has important consequences for the retention of black holes after galaxy mergers, and for the retention of black hole in clusters, in star clusters within galaxies, as those black holes merge, usually close to the center of the cluster. So this is already a very important result to tell us how black holes might evolve during galaxy mergers and how many black holes we might find in globular clusters. Another useful result beyond gravitational waves is that we can get the final mass and spins of the black hole, which has applications both for the evolution of supermassive black holes and of their spin in cosmological simulations, and also for to try to figure out what the final result of a black hole merger in LIGO is, and try to compare it to the actual observed masses from gravitational waves, which is what we were doing with LIGO earlier today, when comparing the pre-merger and the post-merger signal. We know what the masses are in the pre-merger signal. We can use numerical relativity to predict what does it mean that they should be after merger, and then we can compare that with the actual measured masses from gravitational waves. All right, so I'm going to stop the discussion of numerical relativity here and just say, okay, it was a very complex problem. It took decades to actually get to a point where you could put Einstein's equations on a computer, mostly because it's very hard to figure out how to choose your coordinates in general relativity and how to keep your equations stable. And it's very hard because we don't have much intuition as to what happened in general relativity when you evolve a black hole, and also because the equations themselves were initially not in a form that was particularly amenable to numerical evolutions. But today, we can fairly robustly evolve binary black holes, at least at low mass ratio, and generate waveforms for LIGO. And what has to be done is increase the accuracy of these waveforms so that when detectors improve, we're not limited by numerical simulations, and also increase the parameter space coverage so that things like what Lisa might see, for example, can be handled by numerical simulations. All right. Yes?
So in those plots you had of coverage of parameter space is definitely not fully covered. But in the LIGO, we expect to see black hole parameters possibly all over the net.
Right. So yeah, so the way the templates are constructed is, as I was mentioning earlier, you don't use directly the result of numerical simulations. What you do is you take an analytical model based originally on post-Newtonian theory, for example, okay? And you have a few free parameters in your model for whatever should happen during merger that your model cannot really predict because it's post-Newtonian. Okay? Or maybe you make an entirely phenomenological model that is a fit to existing simulations. And then you take your numerical simulations, wherever they are in parameter space, and you compare them to the model, which covers the entire parameter space, right? And you see, okay, do they agree? If they don't agree, either you build a better model or you just recalibrate the free coefficients in your model. Okay? And then you say, okay, can I extrapolate that model to another part of parameter space? And for that, you say, okay, I'm going to run a new simulation somewhere else in parameter space and see if the model still works. You know, does it? I had a model that worked for aligned spin. Does it also work for misaligned spin? Yes or no? And you can just try a few simulations with misaligned spin. And if they work for all of them, probably your model extrapolates well. If they don't, then you better continue working with more misaligned spin simulations. So that's why there's not a full parameter space coverage of simulations. They tend to be developed. First, let's build a model for equal mass systems. So let's run a bunch of equal mass systems. Now, let's see for non-spinning system what happens if I change the mass ratio. So you build a bunch of different mass ratio, but with no spin. And you calibrate your model to that. And then you make a few that have both spins and different mass ratio and see if it still works. But maybe you don't need to cover the entire parameter space as long as they work for the one that you tried. That's sort of the idea. But again, there has been a realization that there was a lot of human bias in the choice of simulations. And so the simulations that are being run more recently actually try to cover the parameter space more equally. And especially, there are methods to actually figure out, which part of parameter space would provide us with the most additional information, which one looked the most different from what we have currently tested. And you can look at that in your model. Where does the model look different from what I've already tested? And then I'm going to run a simulation right there, at the point it is the most different from anything we have tried, and see if it still works.
This kick that binary black holes acquire after the merger, how does it depend on the mass of the black hole, on the mass ratio, on the total mass?
Yeah, so it definitely depends on the mass ratio. I think the maximal one found around mass ratio of a few, maybe 3 to 5, and misaligned spin is in a certain orientation, which it's a weird one. It's a 60-degree angle with the it took a lot of iteration to try. I know you can get very high spin if you have spin that are in the orbital plane, very high kick if you have spin that are in the orbital plane and anti-parallel to each other, but that's not the maximal configuration. Without spin, it definitely depends on the mass ratio very clearly. But it's not a monotonous function. It has a peak. It's 0 for equal mass. It's 0 for equal mass. It's also 0 for infinite mass ratio, and there is a peak in between at a mass ratio of a few. That
more or less what I expected to be.
Okay. Okay.
Probably just a naive question, but are there some parameters for which the waveforms are self-similar? For example, if you obtain for example, for a certain choice of the initial masses or something like this, if you just can scale the waveform?
So there is one that is very simple to do, and that is always relied on, is that you can rescale the total mass of the system without changing anything. Because the numerical simulations, in the absence of matter, it's not true for neutron stars, but for black holes, if I rescale the masses of the objects, the simulation is exactly the same. So that's the one that we always count on. So you do one equal mass non-spinning simulation, but you don't do one for 10 solar mass, 10 solar mass, and one for 30 solar mass, 30 solar mass, because it's the same simulation. It is used differently in the LIGO data analysis because there you have a frequency dependence of the noise, which changes what you care about, but the actual numerical waveform is the same. Now, there are more subtle effects that are not as easily interpreted physically. And what people have been trying to do now is actually use mathematical techniques, singular value decomposition, to find which are the most, the dominant components of all waveforms, and try to figure out what is the smallest number of waveforms that you need to generate to be able to superpose them to produce a full waveform, to do the linear combination of those waveforms to produce the full waveform. And that allows you to actually, it's a very high-dimensional parameter space. You would need millions and millions of waveforms if you wanted to cover it using a standard Cartesian grid. But you can get away with hundreds or maybe 1,000 waveform if you do that kind of singular value decomposition. instead of brute forcing it and doing a standard Cartesian grid on your parameter space. So in that way, there is some sort of degeneracy there, but it's not one that we particularly understand. It's just we look at the models, we see, okay, but how can I decompose it into the smallest possible number of components, and then you go from there. It's a useful trick to reduce the number of simulations, but so far it hasn't taught us that much about the underlying physics. Anything else on black hole binaries? Okay, so now I'm going to look at the part of the problem where astrophysics and electromagnetic observation start to become important, which is when you introduce neutron stars in the mergers. So either neutron star, or black hole neutron star mergers. And the first thing to note, which we already heard about in Sylvia's talk, is that one thing that we want to use these neutron stars for is to measure the size of a neutron star. And the size of a neutron star is very strongly correlated to the strength of nuclear interactions between the many neutrons and still many, but not as many protons that are in the neutron star. The neutron star is about 95% neutrons, maybe, unless the center is somehow made of something else that we don't know. But in the simplest picture, it's mostly neutrons. And depending on how strong the nuclear forces between those neutrons are, you are going to have stars of different radii because the pressure in the core of the neutron star is different. Right? That is what determines whether the neutron star is compact or whether the neutron star puffs up, is how much the pressure in the core of the neutron star is. And so for any model of nuclear physics and how strongly those nucleons interact with each other, you are going to end up with a relationship between the mass and the radius of a neutron star, which you can use. And so if you measure the radius of a neutron star or something related to it, then you can get a constraint on nuclear physics. So that's one reason that neutrons or radius measurement, and ideally even combined mass and radius measurement of neutron stars are very important to us. You can see here quite a few different existing models for neutron star matter. You will see that most of those models which come from nuclear physics are above maybe 11.5 kilometers for realistic neutron star masses. There are many good models with just neutrons that cover the lower radius regime, which may or may not be problematic because currently the LIGO preferred range of radii is towards the low end of the nuclear physics range and further left. So there is not really a tension, but if we want to do simulations that use realistic equations of state on the left of this plot, we don't really have good equations of state to use. At least not things that are not just parametrized equation of state. Okay. And the study of these neutron star mergers has become even more interesting now because LIGO has actually seen a neutron star merger. And you will hear a lot more about that from Samaya's talk next week. But to briefly give you an idea, there has been one neutron star merger which has been observed, which is of more or less compatible with equal mass, but because there is such a large uncertainty in the individual mass, it could be mass ratio of nearly up to 2, which is basically anything a neutron star could be, because we don't expect neutron star much above 2.4 or 5 solar mass or so. And the gravitational waves themselves give you a reasonably good localization in the sky, which is what is shown on the right here. LIGO and Virgo together give you a localization which is the dark green region here. And it happened that at the same time, or at least 1 second later, a gamma ray burst was observed by Fermi, and that gamma ray burst was in the blue region there, which overlaps with the LIGO data. And so immediately, a lot of telescopes were pointed right in that green region there. And that neutron star was basically observed in all frequency bands that we could think of. It was observed in gamma rays. We saw what is probably a gamma ray burst coming from these systems. And the X-rays and optical emission that follow that gamma ray burst. And we see very clearly also radio emission from these systems. And then we saw something that I'm going to talk about a lot more later, which is optical and infrared emission coming from radioactive nuclear reactions, radioactive decay in the matter that was ejected by the merger, which is what is called a kilonova, and that happened a few days to a couple of weeks after the merger. So it's a thing that lasts about a couple of weeks. And all of that was actually predicted theoretically before the merger, and then observed in the aftermath of that merger in August of last year. And we've already seen some of these results in Ariadna's talk on Wednesday. So before I get into what the neutron star mergers look like, it might be useful to remember a few important timescales, and so what we are looking at. The two neutron stars, from the moment they are formed to the moment they collide, it takes about 1 million to 1 billion years. We don't know exactly. There are many different models. It's very poorly understood. It's one of the things that actually we might be able to constrain with more observations of these systems. But it takes a long time. In the LIGO band, the neutron star is only visible for a few minutes, or if it's a black hole neutron star, which is more massive, maybe a few seconds instead. So a much smaller time than the total inspire rate, and that's the only thing that's the only time where we see them. Is that those very last few minutes of evolution. The disruption or merger of two neutron stars, the exciting part of the movies that you might see in conferences, that's about a millisecond, on which you might have spent 6 months of computer time. And then over maybe 10 milliseconds or so, you form a disk, which is nearly axisymmetric. And that disk has a lifetime of, again, a few orders of magnitude longer, a few seconds, maybe 5 to 10 seconds. Right? And we know that short GRBs, that's not a theoretical prediction, that's the actual observed short GRBs have duration of up to a couple of seconds. That's actually the definition of a short GRB. So that's something that we know from observations, but not from simulations, because we haven't been able to properly simulate the production of a short GRB in simulations yet. Only approximations to it. So let's look a little bit at what the physics of these neutron star mergers are. And I'm going to first look at the inspire, then at the actual disruption and merger of these systems, and then at the post-merger evolution, because there's different important physics at the different stages of this evolution. For the inspire, the one thing that we are going to be sensitive to, which is different from black hole mergers, is the size of the neutron star because of the tidal distortion of the neutron star in the gravitational field of its companion, whether the companion is itself a neutron star or a black hole. So you can imagine that if I have a neutron star around the black hole, this is the black hole, my neutron star far away is going to be nearly circular. But as I get close to the black hole, it's going to get elongated. And as that elongated neutron star rotates around the black hole, it has a non-zero time-varying quadrupole. And a non-zero time-varying quadrupole means more gravitational wave emission. And because it occurs at the same frequency as the orbital evolution of the binary, it adds coherently to the gravitational wave emission. It doesn't average to zero. The energy in that emission is non-zero. And so this leads to a correction to the energy lost to gravitational waves. It only matters when the objects are very close together. Or another way to say that is that it's a correction which comes at 5 positons in order, or at order V10 over C10. If you compare to everything we've talked about so far, we haven't gone further than 2.5 in anything I've talked about so far. So this would seem like a fairly small effect. It actually comes with a pretty big numerical coefficient in front, so it's visible, but only during the last few orbits. So you can see it, but only during the last 10 orbits or so, maybe. And so that is the static tide. It's the fact that the neutron star in equilibrium in the gravitational potential of the other object is distorted. There are other effects that depend on the size of the neutron star. there can be resonances between excitation mode of the neutron star, so whatever the ringing mode of the neutron star is, and the orbital evolution of the system, which excites the neutron star and lead to the production of more gravitational waves. And that can enhance significantly tidal effects, but only during the last maybe couple orbits of the system. And there are also many resonances between multiple ringing modes of the neutron star. It takes at least 4. It's been shown that with 3 the total effect is 0, but at least 4. And those may dissipate energy, lead to a heating of the neutron star and dissipation of energy, and possibly a change in the orbital evolution of the system. And so those could cause changes in the evolution of the binary long before merger. The first two have now been studied through numerical simulation, and we have models for them that are being used by LIGO, or at least model calibrated to numerical simulations, which do include both of these effects. The third one is more uncertain, because we know that these resonances might occur, but we don't know how much energy they dissipate or what the practical effect is. And they are very sensitive to the exact structure of the neutron star, which means that actually knowing when they happen and how often they happen is very difficult. So we don't really know what the effect of the third one is. It's obviously not enough for us to not detect neutron star when they actually merge, because we have detected the neutron star, so that's a relief. Because at some point there was a claim that it might be enough of an effect that it would ruin the waveform that we were using. But the exact nature of these still remains open for studies. So this is what the tidal effect looks like in these systems. In blue, this is all equal mass systems, so with most of them with no spin. The blue curve shows you a binary black hole. And let's start with the red curve, which is a non-spinning black hole neutron star. The waveform for most of the evolution looks very much the same. And then you get within a few orbits of the peak of the merger, and you see that the red starts to evolve faster towards merger. And that's the effect of the tides. It's just extra energy loss due to gravitational wave emission. And then it also cuts off at a lower frequency and at a lower amplitude, and that's because the neutron star is ripped apart by the black hole, as we will see later. The white curve is for 2 neutron stars instead of a black hole and a neutron star. It's the same type of neutron star that in the red curve, so the effect is just twice as big. That's fairly simple. And then in the green curve, the neutron star is spinning. It's spinning with in the same direction as the orbital angular momentum of the system. And so as for binary black hole, that creates also a hang-up effect this one, yes, it's merging earlier, so it's actually spinning in the opposite direction from the angular momentum, meaning that it's going to merge faster. So yeah, it's merging faster than the other ones, but that's the effect of the spin. So this shows you that the effect of the spin, even on a neutron star which is not spinning very fast, can actually be easily larger than the effect of tides. And that's why LIGO has to make some assumption about the spin of neutron stars when it's trying to measure tidal effects, because otherwise tidal effects become a lot harder to measure. So here's what those tidal effects have been measured in LIGO, in the one event that LIGO has observed. And here's the type of constraints that they get on the mass-release relationship of neutron stars. You can see that, roughly speaking, you constrain the size of the neutron star to being within 9 and 13 kilometers, with a favored region somewhere between 10 and 12, more or less. But that's, it's not an extremely accurate measurement, but it's just one event, and LIGO is going to be able to add tens of events, and under the assumption that all neutron stars have the same composition, you can add them together and reconstruct the equation of state of neutron star by using all of the available events. And so presumably when LIGO gets tens of neutron stars, those error bars are going to become much, much smaller. And that's the main objective here. At this point, it's already a very nice measurement. It's actually better than we were expecting for a first neutron star merger. But it's not really constraining on nuclear physics more than other measurements of neutron stars had been before.
Can they find the radius of
The radius of the post-merger remnant?
yes.
So you could get information about the post-merger remnant, including, as we will see, its ringing frequency. But that's gravitational wave emission, which happens at typically 2 to 4 kilohertz. And LIGO becomes a lot less sensitive in that region. And on top of that, LIGO, as it is now, hasn't reached its design sensitivity at high frequency yet because it hasn't increased its laser power. And so at the time of the detection, the high frequency sensitivity of LIGO was not that great. So it got some, some upper bounds on what the total amount of gravitational wave energy in the post-merger remnant was, but they are not particularly constraining. They are above what you would have expected the merger to produce. And there is certainly no measurement of the actual frequency of the waves. We don't even know for sure whether there was a neutron star formed at first or whether it collapsed to black hole. The argument that it didn't collapse immediately from a black hole comes from electromagnetic observations and no understanding of what should happen to lead to those electromagnetic observations. But the gravitational waves give us no constraint on whether the neutron stars collapsed immediately or not, because we don't see any signal after the merger. We only see the pre-merger signal. Anything else? All right. So that's what LIGO has been able to do with the one existing neutron star event, just using gravitational waves. And again, we will hear a lot more about the observations next week. What I'm going to do for the rest of this lecture is look at what are the main things that happen during a black hole neutron star merger and maybe a neutron star merger. And then on Monday, we are going to look at all the physics that matter after the merger when you form an accretion disk around a black hole or a neutron star, and which is the phase where really you are going to produce all of those interesting electromagnetic signals. And we will also look at the nuclear physics involved in forming heavy elements in neutron star mergers. But first, we can look at the merger. And the merger is easier to understand because it basically only depends on gravity, Einstein's equations, hydrodynamics, the evolution of the fluid in the neutron star, and whatever your choice is for the equation of state of cold matter in the neutron star. So you don't have to worry about what happens when the neutron star gets heated, but what happens when it emits neutrinos or absorbs neutrinos and changes its composition. You only have to worry about the properties of cold neutron stars in beta equilibrium. It simplifies the problem a little bit. For black hole neutron star, the most interesting type of event is shown here, in which your neutron star is tidally disrupted by the black hole. It is ripped apart, and then you end up with some material which is ejected into the surrounding interstellar medium, and some material which forms a massive accretion disk around the neutron star, around the black hole remnant. This is a particularly favorable case for disruption. It's the highest black hole spin that has ever been simulated. It's not really what we expect to see at first, but it makes for more mass ejection in the movies. So if we want to understand the disruption process of neutron stars, we have to try to figure out what determines whether a neutron star is actually disrupted by its black hole companion, or whether the neutron star just plunges into the black hole without being disrupted, like what would happen around a much more massive black hole. So if you have a neutron star falling into a supermassive black hole, you expect it to just fall in. If you have a neutron star around a solar mass black hole, it's disrupted. What sets the difference? Well, the disruption is actually a principle which is fairly close to the Hill radius that you've already seen in, I think it was Phil's lecture, right? That when the tidal forces acting on the neutron star, which is roughly speaking the difference between the tidal force at the surface of the neutron star, and the gravitational force at the center of the neutron star and the gravitational force at the surface of the neutron star, when those forces are roughly equal to the self force, the gravitational force of the neutron star on its surface, then you might get disruption of the neutron star. That's when those two effects are roughly balance each other. You know, the black hole trying to stretch the neutron star, and the neutron star trying to keep itself together. And you can make an estimate for both of those in Newtonian physics. Let's not do any relativity because it doesn't matter here. And you see that the difference in the acceleration due to the black hole is roughly the derivative of the gravitational force, which is 2m over d cubed, times the radius of the neutron star, so the distance between the center and the surface. While the gravitational force of the neutron star is the mass of the neutron star over the radius of the neutron star square times the gravitational constant. If you equal those two, you get a relationship between the distance between the two objects, the mass of the object, and the radius of the neutron star, which is roughly speaking where you expect the objects to the neutron star to be ripped apart by the black hole. The coefficient there depends a bit on the assumption that you make for the rotation of the neutron star. It can be 2, it can be 3. It's an order of magnitude anyway because we're only doing Newtonian physics here.
So does it, you said that it depends on the rotation of the neutron star, but what about also the black hole, like in that number thing?
So yeah, so a rotating black hole will have a different metric around it, different, if you want, gravitational field, and different tidal effects acting on the neutron star than a non-rotating black hole. So you can do the same calculation for rotating black holes, and you get slightly different results, yes. This is just to get an order of magnitude of where it's happening. The way we actually determine in practice whether a neutron star is disrupting or not is by doing the simulation and seeing whether it disrupts. So this gives us a rough idea of where to look for the boundary between the two. It's definitely not an exact result, not even close. It gives us an order of magnitude. It definitely depends on the rotation of the black hole, yes. Okay, so disruption distance is roughly what we have just seen. It depends on the mass ratio of the system and the radius of the neutron star. One thing that simulations have told us is that when the neutron star starts overflowing its Roche lobe, starts accreting onto the black hole in general relativistic simulations, that accretion is always unstable, meaning the neutron star doesn't start accreting and then move away slightly from the black hole and stop accreting, like can happen in some Newtonian system. The neutron star starts accreting and then it goes unstable and it just blows away, as we have seen in the movie. Some matter is ejected, some matter falls in, but there is no stable mass transfer between the two objects. There can be transitional phase of accretion if you have a very eccentric orbit. So if you have a star coming close to a black hole and then moving far away on an eccentric orbit, then you can get a little bit of matter being accreted as the star passes at periastron, and then it moves away and manages to survive. It can happen. You have to sort of fine-tune the parameter of your simulation if you want to get that, but it's possible. Not expected to be common in actual astrophysical simulations, astrophysical situations. Now, what we have to compare these disruption radius with is what is called the innermost stable circular orbit of the black hole, which is the distance from the black hole at which the closest to the black hole that you can be on a circular orbit, a stable circular orbit, and not fall into the black hole. If you get closer than that from the black hole, circular orbits are unstable or just do not exist, depending on how close you are. And so a small perturbation of your orbit will lead you to falling into the black hole. So there is no circular orbit that remains there outside of that ISCO. And so if you reach the ISCO, the innermost stable circular orbit, without disrupting, you are just going to fall into the black hole. If you disrupt outside of the ISCO, you are going to be ripped apart. And the ISCO distance is, depending on the spin of the black hole, between 1 and 9 times the gravitational radius. So for a maximally spinning black hole, if you have prograde orbits, it's 1 time the gravitational radius of the black hole. And for a counter-rotating black hole, it's 9 times. So it's a pretty strong function. It can be an order of magnitude difference depending on the spin of the black hole. And that's another way the spin of the black hole matters in these things, is that actually how close you can get to the black hole without falling into it actually depends on the spin of the black hole pretty significantly, actually more than the location of tidal disruption. So that's your condition for a neutron star to disrupt. And whether a neutron star disrupts or not is very important for us, because if it does not disrupt, if it just falls into the black hole, there will not be any electromagnetic signal coming from that system. And also it becomes very hard to measure the imprint of the size of the neutron star on the gravitational waves. We really want the neutron star to be ripped apart, because that's when interesting things happen. That's when we can see something. And what we learned from this comparison between the disruption radius and the ISCO separation is that, well, not surprisingly, it's easier to rip apart a big neutron star. It is not as tightly bound. So a big neutron star is easier to destroy. You can see that the mass of the black hole comes to the 1/3 power in the disruption radius, but the ISCO scales linearly with the mass of the black hole. And so if you have a high mass black hole, you are less likely to disrupt the neutron star. If you want to disrupt the neutron star, you are better off having low mass black holes. That may be a problem for us if the black holes observed in black hole neutron star binaries are similar to the ones observed in black hole binaries. A 30 solar mass black hole is nearly never going to disrupt a neutron star, as we will see. A 5 solar mass black hole, on the other hand, that can happen. So if black holes are more likely to be at 20 or 30 solar mass, then it's going to be very difficult to get disruption from neutron stars. If, on the other hand, those 20, 30 solar mass black holes observed by LIGO are mostly an effect of the bias of LIGO towards seeing higher mass objects, then that's fine, because we'll probably see mostly things like in the Milky Way, in black hole neutron star systems, and those are lower mass black holes. So if you put the units back in those expressions at the top, you end up with the fact that the disruption radius actually doesn't vary much with the parameters of the object, because it depends on the radius of the neutron star, which doesn't change much. It's pretty well constrained, and then the rest is to the 1/3 power. So for realistic systems, it's not going to be a huge difference. It's always about 20 to 30 kilometers. So it's a pretty small distance. You have to get pretty close to a black hole to disrupt it. And then the ISCO varies more, because it varies linearly with the mass of the black hole, and you have an order of magnitude change depending on the spin. So that gives you somewhere between 8 and 400 kilometers for the mass that I chose for the black hole here, 5 to 30. So you can get, definitely those are comparable at least. For realistic black hole neutron star binaries in the LIGO band, you can definitely have configurations where the ISCO is outside of the disruption location and you don't disrupt the neutron star, or the ISCO is inside and the neutron star is destroyed. Both are possible. Right? And so the dependence on the spin of the black hole, again, if you have a high spin and in the same direction as the orbital angular momentum, it helps disruption. And if you have a low spin, or even worse, an entire line spin, then it makes disruption harder for you, because the ISCO is farther out. And that is shown, for example, in these two visualizations of a black hole neutron star mergers from simulations. The left is the mass ratio 6 systems with a non-spinning black hole, and the neutron star is just going to plunge into the black hole, leaving nothing behind. On the right, you have a higher mass ratio, which should make things harder to disrupt the neutron star, but we put a high spin on the black hole. I know the tail of the neutron star is actually disrupting, and that end of the neutron star is actually going to form a disk and form a nearly circular orbit there. Part of it, and part of it is even going to be ejected into the surrounding medium. So it's not very much of it, and this all happens very close to the black hole. But because the high spin of the black hole allows you to survive disruption, even if you are just outside of the horizon, you can actually keep matter outside. And to summarize, you can look at what would it take to disrupt a neutron star in a black hole neutron star merger. So that's one visualization of that. You can consider a neutron star like the one that have just been seen by LIGO, it's a 1.35 solar mass. And you've changed the mass of the black hole and the radius of the neutron star, mass of the black hole on the vertical axis, the radius of the neutron star on the horizontal axis. And you can ask yourself the question, for those parameters, what black hole spin do I need in order for the neutron star to disrupt? So there is a minimum black hole spin that is needed to disrupt the neutron star. Right? And at low mass ratio and high neutron star radii, nearly any black hole is going to disrupt the neutron star. But if you believe that black holes are more likely to be close to 10 solar mass, and neutron stars are 12 kilometers in radius, which is already decently big, suddenly you need a black hole spin of at least 60% of the maximum value in order to disrupt the neutron star. So then maybe most neutron stars do not disrupt. Now, the interesting thing about this prediction, which is a fit to numerical simulation, is that if we see a black hole neutron star and we see an electromagnetic signal associated with that, which has to come from the disruption of the neutron star, we can immediately get a cut through parameter space. We can know, oh, there was a rapidly spinning black hole there. Alternatively, if we know that we should have seen something and we don't, we might be able to put a maximum value on the black hole spin. But that's not as clean cut as you have to prove that you didn't see an electromagnetic counterpart and that there should be one. And the last part is tricky because maybe you were in the wrong orientation, or who knows. So it can be tricky to do it if you don't see anything, but if you do see an electromagnetic counterpart, you get a constraint on the properties of the black hole and the neutron star, which can complement what you get from gravitational waves. Okay, and the other aspect of gravitational waves that is useful to get from this disruption of no disruption of black hole neutron star binaries. So the other information that you can extract from this disruption or no disruption in black hole neutron star binaries is that if the neutron star disrupts, the gravitational wave signal is cut off at high frequency. So again, this is a spectrum of the gravitational wave amplitude. The blue curve shows you a black hole binary, and the green curve is a disrupting neutron star binary. And the disruption means that the late part of the merger, the plunge of the neutron star into the black hole, does not exist, is cut off. You don't have a clean quadrupole anymore, but you have a ripped apart neutron star that doesn't have much of a quadrupole. And you cut off the high frequency signal here. And the frequency at which that cutoff occurs is strongly dependent on the properties of the neutron star, and it's around 1 or 2 kilohertz. So it's difficult to detect because, again, LIGO is not great at 1 or 2 kilohertz, but it is a clean mark of the size of the neutron star that you can hope to use. And it's a little bit better than neutron star, for which the merger is at more like 3 to 4 kilohertz, probably, the post-merger signal. And that also depends on the spin of the neutron star. You can see a spinning neutron star actually disrupts more easily, and so it cuts off at a lower frequency. Okay, so I think that I'm out of time, right? For now? Yes. About? So I'm going to leave what happens after the merger in those black hole neutron stars for Monday, and also the merger of neutron stars. And then we will see all the physics that happens after the merger, so the magnetic fields and neutrino physics that is important for all the electromagnetic signals that Samaya will be covering next week as well. And so that should lead you to transition easily into those talks, having seen what the theoretical side of it is. So any other question on the black hole neutron stars or anything else I talked about today?
Let's sum it up.
You said that in these mergers they can lose typically 5 to 10% of the energy in gravitational waves. Mm-hmm. But is there a theoretical upper limit to how much they can lose?
I'm not aware of a theoretical upper limit. I think the upper limit so far has been obtained by looking at we kind of know which configurations produce the most, and then did a numerical simulation of that configuration. For instance, you have a pretty good. You could put a theoretical limit on how much gravitational waves last in the PN regime, where you trust your analytical approximations. But then the merger itself is very hard to get, and so getting that part right is complicated. But you know which simulations to do to find the maximum, and you can do that simulation, get the merger, and add the post-Newtonian part and the merger part, and figure out what is the actual value of the energy last. And that's how those current upper bounds were derived. at least the ones I'm aware of.
Well, more. Well,
So in black hole neutron star, black hole neutron star merger, can the gravitational wave emitted during the merger kinematically affect whatever mass is not affected at the start of constructed?
So, I mean, the problem is the curvature of space-time and its change in the near field of the black hole and neutron star definitely affects the neutron star evolution. So in that sense, yes. I wouldn't call it a gravitational wave because you're actually at the place where you have strong field and nonlinear interactions, while the gravitational waves is a concept which only really find far away at the point where it does not actually influence things anymore. So it depends how you want to interpret the question, I guess. But I mean, the chances of curvature definitely has an effect on the dynamics of the neutron star and of the remnant of the neutron star. Yes. So in that respect, yes. Should we, Phil?
But it is the fact that the mass transfer is always unstable, mostly just because you're losing angular momentum at such a high rate due to the gravitational waves, or is it sort of a more subtle GR difference with Newtonian physics?
My understanding is that it's mostly the first one, that most of those disruption events occur at a point at which you are already moving radially reasonably fast. And so even if the mass transfer would tend to push you out, it doesn't compensate the gravitational wave-driven inspire. So that is my understanding of it. I'm not sure there has been a detailed study of exactly what, that point because it's probably hard to exactly measure in a numerical simulation in general relativity because anything measured in the closed region is tricky. But that's my understanding of it, at least, is why the Newtonian simulation did not have that effect. Yeah, that's what I would say.
So would having a bunch of black hole mergers in the early universe produce a bunch of gravitational waves, and would that have an impact on the expansion history? So I'm just imagining you have a bunch of the energy density of the universe matter, but then if you keep on merging all these black holes, you'll send it to the radiation components.
I mean, you would need to have a significant fraction of your of the energy of the universe in black holes, which seems difficult.
What is the estimate for like massive black holes?
I mean, some people have tried to use it to do dark matter, but even there, it's tricky. And I think that by now, actually, with Lansing experiments, it's at least the most common form of it are pretty much ruled out.
So it's under 1% of baryonic matter.
Well, dark matter is bigger than baryonic matter, so I'm not quite sure what the strongest constraint right now on the mass of free-moving black holes in the universe is. There are definitely some. They are somewhat mass dependent, so you have to make assumption about what the masses of those free-moving black holes are. But I mean, I know that there are constraints that come from Lansing experiments. I do not know exactly what they are. But those are also those are not merging. Also, they are like they are black holes that are just moving through the universe. So they actually don't lose much energy in gravitational waves. So it wouldn't affect, in that respect, the expansion of the universe, except for the fact that they have mass. And so it has been thought about for dark matter, but I wouldn't say it's the most favored theory right now for dark matter.
well. Thanks a lot.